start whenever you want.
Thank you. So first, let me thank the organizers. They have done a wonderful job for bringing everyone all together, and wonderful discussion, which has lasted quite late in the evening as well. So I will talk about non-local gravity. I'll give you a brief motivation. I will talk about a little bit of resolution of curvature singularity and some of the open issues. And as you can see that as a drawing of an elephant, so to be honest, non-locality is a big elephant in our room. We don't know which part of this elephant we are touching, but whatever we are touching, we are trying to figure out some bit of information, some bit of physics. But the more we closer we go to the elephant, we find that the skin is really fractal, so it has more feature in it. And hopefully, I mean, we are trying to understand some of these features, some of these from corpuscular theory, as perhaps Gia has spoken about, and some of the people who are talking about also from the point of view of string theory. So this is what we want to understand the nature in the short distances in the UV. Now, let me thank some of my collaborators. I have been working with many collaborators on the subject. So first work, which we started with Warren Siegel and Biswas, and then Robert, Ivan, Alexis Sarabinsky, Koshilev. We have been working together with Luca and Stravan both. So perhaps you would realize that if you take a very simple observation, nothing profound, but take a Dirac delta distribution, you differentiate that n number of times, you would still get back your Dirac delta. It means that you have a Dirac delta has a point support in your space-time. But suppose you take a non-local operator like exponentiated, e to the power delta x square, you differentiate Dirac delta, you get a Gaussian support. So it doesn't have something. So it tells you that if you have something exponential with all the series, the full derivative, if you take into account, then somehow you don't have a point support, but you have a Gaussian support. So a very simple observation, but maybe this leads to many of the results which Jens has been talking about and Koshilev was talking about yesterday, and many other people have been talking about in this workshop. But since the workshop is also about quantum mechanics or quantum gravity, so let me twist the story slightly from quantum side. And I postpone the gravity part later. Now, quantum mechanics, it has been extremely successful. And we want to essentially marry this both quantum and gravity. One of the features of quantum mechanics, which can never be replicated in classical mechanics, is your quantum superposition. And this is the one, this connects your Hilbert space, a completely abstract space, with this space-time in some sense. So Schrodinger's cat, dead and alive, both are simultaneously existing for us. And as a consequence, a simple consequence is that you can create spatial superposition of given mass. Of course, I mean, maybe in the evening we will hear from Roger Penrose. Maybe he has his own view. He would say wave function collapses as the mass grows, but somehow no one has been able to prove it. Neither he himself has ever been proven it in a mathematical way. But if you think about the quantum mechanics, if the quantum comes first, then what's the meaning of classical singularity? Given a wave function, it will always try to spread out. The singularity, point singularity, or even ring singularity, or even defects, and all these things in a quantum picture, does it really make sense? And that itself is a question which maybe one has to, re-ask ourselves in some sense. Another feature of quantum mechanics, which can never be replicated in a classical world, is the entanglement feature. And we see that from condensed matter system to high energy physics to black holes, ADS, whatever you pick up in any example in nature, if there is a quantum interaction between two systems, this entanglement is inevitable. And yesterday and day before yesterday, we have been talking about the nature of vacuum. And if you shake the vacuum, if you excite the vacuum, what you get? You get a pair production of electron-positron from the vacuum. The famous Schwinger pair production. These are entangled pair. And you see that as soon as you disturb the vacuum, you see this entanglement feature coming up. The off shell becomes on shell, and you can really see this entanglement, building up gradually. And many times people we talk about entropy. Now, entropy in a quantum system, the only entropy is your entanglement entropy. If you take the full system, it's a pure state, and it has no entropy. So only entropy comes in when you try to, again, subdivide the system, A, B, C, D, and then you can talk about the relative tracing out some of the degrees of freedom, and you get the entanglement entropy, which you can recast in the von Neumann's entropy. Some of these mathematical things, we know it very well, how to define entanglement entropy. But the key thing is that you're trying to build up some quantum correlation between two space-time points, or multiple points in space-time. So that's the key thing. So now let's come back to gravity. Now let's do the simple experiment, which many people like to think about. You take Alice and Bob. Let's take them to be a spin system. You embed a spin, so these are quantum system in some sense, and you try to bring them together, the Alice and Bob. And let's say that we are in a classical general relativity. Nothing beyond that. Now what would happen? So at some point, at some distance, what will happen is that you will start trapping it in a sense that even the light cannot come out of the surface. Everything is focusing inside. You create a trapped surface in general relativity. And and after a while, what will happen? So if you go through the movie, the trapped surface starts expanding. You hit the event horizon. So essentially, apparent horizon eventually will become event horizon, and the system will start radiating via Hawking radiation. So, in classical general relativity, we also know that the collision between Alice and Bob, what it will do, no matter whatever whatever we do, we will eventually form a singularity. So there's a part of the manifold in the space-time will not exist, and that's the singularity for us. Yeah. So there's something good, something bad. Something good will come in the next slide. And I think this is, this is something which Gia had already highlighted it. Even in general relativity, there's some kind of non-locality. And the non-locality comes again from the information side. You see that, yes, Alice and Bob had gone inside, but an observer who is sitting outside of the black hole would immediately see that there is a Bekenstein's entropy. So the information did not get lost in some sense. The information now got transferred into the entropy of a black hole, which we know very well. It goes by the area over Newton's constant. So even a semi-classical level, you see that once you put in quantum mechanics, there is some amount of non-locality, even in general relativity. But there is unsatisfactory part too. The unsatisfactory part is that, of course, from outside, I cannot track Alice and Bob. But if I say that if I jump inside my horizon, again, tracking this Alice and Bob is becoming a nightmare. And that becomes essentially my cosmological singularity, because once you jump inside the horizon, you go inside the horizon, your metric becomes time dependent. And many people have thought about this, that maybe we might be living in a big black hole ourselves in the universe. It was Mukhanov who kind of like wrote this paper way back in the 80s. Now, of course, there are various ways. Now you can ask, I really want to track Alice and Bob. So the same Alice and Bob, which I collided them, I want to track them. Yeah. Now, of course, I need to go beyond GR. And many times we have discussed in this workshop that one of the consistent theories indeed is string theory. And it's possible to track Alice and Bob in the context of string theory. Of course, now Alice and Bob will lose its identity. It will be essentially excited into strings, but nevertheless, I can, at the most fundamental level, I can think about either it's an open string or closed string, there is a scattering happening. And we have learned from various talks already, and we know that in string theory, what happens is that to certain degree, you can track the problem, not all, and eventually you will see that this problem is intractable even in string theory. The one which I'm talking is intractable, but nevertheless, I just want to give you the flavor. The flavor is that essentially you're talking about interaction in the string, closed strings. Now and we have heard that string theory is ultraviolet finite. The way it becomes ultraviolet finite is that if you look into the amplitude, what happens is there's a part which is a partition function, and there's a part which is the Green function. Both of them lead to softening the behavior. One which softens the behavior in the low energy limit, that is because that is essentially the partition function contribution. And the one which softens the UV comes essentially from the Green function. And let's say that I want to recast this entire non-locality in the word line formalism. In the word line formalism, what will happen is that in a proper Schwinger parameterization, the information about the Green function lies in this function T of t. And you can take T of T to be various forms, and eventually you would like to be in the form where we have already spoken about that it should not have any poles in your complex plane. You can live with the essential singularity, but essentially effectively this combination has to be an entire function. And these are the calculations. Many people have done it in past: Gross-Mende, Koplanowski, Dixon, Lewis, and these amplitudes are computed at the saddle point limit. But barring so, the non-local feature is very much present in any of these calculations. But now the extrapolation is that from the worldsheet, you are taking it to the world line. Now, how good this approximation is, how good this validity is, of course, these are questionable issues. But why am I going towards this world line approach? The reason is, if I really want to track Alice and Bob inside this black hole, it's really a nightmare, even in string theory. You have to take into account of time-dependent background, and the problem becomes intractable. At least I don't know how to solve it. And to my knowledge, I think it's not very well settled yet. So from the space-time perspective, then if I want to solve the problem, maybe this is hoping that sometimes it will simplify my calculation. Yes, I can do that. In general relativity, I know that it's essentially in a Minkowski space is nothing but a two-derivative theory. But being massless, you can have infinite derivative. Nothing stops you. There's no symmetry which prohibits you from writing down infinite derivatives. So essentially box here, I can replace by A of box. And similarly, these A, B, C, D are the only 4 terms through which I can recast GR in Minkowski space. But on top of that, I can dress them covariantly by adding infinite derivatives. Nothing stops me. So that gives you essentially non-local gravity. It will have a term which is Einstein gravity, R square, but with non-local form factor, Ricci tensor, and the wild part. Yeah, and you want to recover the local limit, the GR limit, in the limit when MS goes to infinite. Yeah, you want to see that at the end of the day, you don't want to spoil the GR's predictions. Now, this is a little bit technical. I will skip through this because it's related to the fact that how do you obtain the propagator and things like that. Maybe in the discussion session we can discuss. But the key point is that between the two space-time points, if there are two masses, MA, ME, if they are scattering, what are the degrees of freedom which are propagating? And as we know, there are 2 degrees of freedom: spin 2 component and spin 0 component. These are the components which propagate. And in the infinite derivative gravity, essentially these 2 components, they get modified. This is obvious. This is expected. And the way it gets modified by this function A of minus k square, and A of minus k square appears here, as you can see here. And rest of the BCD term, you can trace, you can trade it off with the help of Bianchi identities and things like that. So anyway, so this is the part which you would like to behave like an entire function, exponential of an entire function, which doesn't introduce any new pole. And the rest of the quantity you see is exactly like your GR. So you want to recover your GR limit. That's the whole point. So, and a similar thing, similar prescription can be carried out in the context of ADS as well. And Alexei had talked a little bit about that yesterday, how to do that. And in principle, one can do it in ADS and also some in de Sitter as well. But I will not go into all the details. Let me highlight to the equations of motion. And I thought that maybe I cannot solve the string problem of Alice and Bob. But when I thought that, okay, maybe non-locality in space-time will simplify my life, I immediately realized that no, it doesn't simplify my life. This is the equations of motion, which is a page-long equation of motion. It makes my life even more, even worse. So it's a highly nonlinear and highly non-local. So maybe I didn't get enough from my trade-off. But nevertheless, I just didn't give up the theory. I just started pursuing it a little bit more to see that to what extent can I get the leverage. So I started solving the equations of motion. So one thing which I realized, and I think Jens pointed out very nicely, that all the interactions, so essentially, if you look into the non-local theory, if you take away the interaction term, effectively it is it's the local theory. There's no difference. You can always trade off the non-locality from interaction to your kinetic term. So one of the reasons we thought, okay, how about we localize the action? If you localize the action, then all the non-locality is in your perturbation. If you perturb it, then you will start seeing the non-locality, because that's the place where you start seeing the interactions. And it paved us off. So by localizing, this was a trick which we used for the first time, to my knowledge, in the paper with Warren Siegel and Biswas. way back in 2006. And what we in the context of cosmology, we use it. And what we found is that you can resolve the cosmological singularity. Instead, you get a bouncing universe with homogeneous and isotropic with a positive cosmological constant. Now, you can repeat the same calculation for negative cosmological constant, you get a cyclic universe. And then many people have taken this feature. Now, maybe Alexei tomorrow will be talking about cosmic inflation in this context, and many things have happened in the context of cosmology. The other possibility, which I think to some extent Jens already pointed out, that what happens if you go to the linearized limit? You can show that there's no singularity even at the point light. You can show that even the rotating, if you have a rotating disk, there's no, you can resolve the rotating singularity in a linearized limit. And also Frolov and Jens have computed that if you take a membrane, again, you can resolve the singularity. My postdoc, Ivan, he looked into the cosmic strings, rotating strings, and also Jens had looked into it, these kind of problems, and shown that you're even with the defect, you can resolve, you can smear out the singularities. Yeah. So just go back to the one problem of the, again, Alice and Bob, because we'll come back again later on. So suppose I want to understand now what is the gravitational interaction at the tree level. Alice and Bob, they are interacting. So what, it's a simple Newtonian potential. And what happens is that instead of 1 over r potential, you get the error function. And error function, as you know, as if you take the argument to be less than 1, error function, the r will cancel out with 1 over r, and you get a smooth gravitational potential. And of course, now you can ask, and people have discussed that, well, there's a plethora of entire function you can choose, and which one is the right one? Of course, there's theoretically, there is no bias, but of course, experimentally, you can always put a certain limit. And so not all kind of error function, not all kind of entire function will work in your favor. What will happen is that you can see that you will start seeing some feature in the Newtonian potential, which you can actually verify it to some degree with the experiment, Seattle-based experiment from Adelberger. And so to cut the story short, the blue line is a GR, and the brown and the maroon line is this one, which matches very well. That is the error function. And there are other choices of entire function you can pick up, but they start giving you some kind of oscillatory behavior. So in some sense, you can bring experiment as well. And this is what we had worked out with Koshelev some time ago in 2016. But if you look into the core of all these examples, and it doesn't matter whatever example you pick up, in the UV, there's some universality builds up, and that universality is that the core becomes conformally flat in the region where your linearized limit is valid. And the linearized limit is valid for not for all masses, but for certain masses m, the scale of non-locality such that mms is less than m Planck squared. That's the linearized limit. That's the place where you essentially have a mass gap, that as long as mass is below this, satisfy this inequality, you can resolve the singularity. Of course, now you can ask the question, what happens if you exceed that limit? We don't know yet. But there are some progresses have been made, even in the classical equations of motion. You can try to solve order by order, or you can take the known solutions and ask whether those known solutions, such as 1 over r to the power alpha, which is highly singular when r approaches 0, whether that satisfies the entire equations of motion for the full action. And the short answer is no. It's technical is quite hard, but the short answer is that it doesn't satisfy your classical equations of motion in presence of t mu nu equals to 0. So it's not a vacuum solution for this infinite derivative theory of gravity, which is kind of like expected, nothing going beyond expectation. Now, if we just concentrate on the non-local part, this is the part where in the UV, these are the terms on the action which will dominate. And if you look into the solution, very interesting solution appears. And that is nothing but your Robinson-Bertotti solution metric. So this is the metric which you recover, and such that your Kreshman is constant, your combination of r mu square is constant, given by your scale of non-locality, and the Ricci scalar is 0. And some of these things I've worked with Luca, with Alexei Koshelev, Gaetano, and Joao Marto, who is also present here. So now again, go back and ask the same question, what happens dynamically? And this is the part of the problem which Frolov had looked into it. What happens when you take these two masses, you boost them essentially in the Penrose limit, what really happens? So I looked mostly in the static kind of problem, but Frolov looked into this boosting problem, which I find is quite interesting because it really goes back to the question, what happens when I take Alice and Bob and I collide them? So in this picture, what will happen is that, yes, you collide them. So in this picture, you don't form a trapped surface, you don't form an apparent horizon, and eventually you also don't form an event horizon. Your metric potential is always less than 1 here. Metric potential is less than 1 outside here. So effectively, gravity gets weakened to some extent. But nevertheless, you still form a bound system, a self-gravitating object, which you may like to call it like a non-local object, non-local compact system. And the property of this non-local compact system is such that it is the size, it is not as compact as GR, Schwarzschild black hole, but slightly more inflated. And this is the place where things become interesting. So essentially, you can think about the non-locality somehow, pushes it outside your GR limit of Schwarzschild black hole. So, but this is your whatever I have spoken about in the linearized limit. But maybe you can speculate. Although there is no solution yet, it's just a hint. Maybe a classical black hole like astrophysical black hole, solar mass black hole will be something like that. That you will in the core. Maybe there is a way to resolve the singularity, and as a consequence, you can track Alice and Bob in this formalism. Of course, no one has shown it yet in a complete, fully nitty-gritty details, but this is the kind of expectation we have. So in some sense, you can essentially, even if you go inside this horizon and you can ask about Alice, Bob, and many other such pairs, you may be able to track them very well in a way that you can even compute their interactions, their entanglement entropy, and all sorts of things. And you would expect, so this is a part of the expectation, that in GR, it will simply keep rising, but in the context of non-local gravity, maybe you will hit some constant number. It will saturate, not the constant, but it will saturate the entropy. As I said, that you can solve the ring singularity in a very similar way. How much time do I have before I go into Francesco?
You have 9 minutes.
Oh, okay, 9. Okay, so then I can go a little bit slowly as well. So good. So, in a very similar spirit, we also look into the ring singularity, which is kind of like very, very interesting, because in GR, what happens is that suppose you have a rotating object, yeah. Effectively, if it has a rotation, and let's say a point source, you have a point distribution, it will give you the length theory metric. So this is the kind of metric it will generate you in the GR in the linearized limit. Now you can ask a similar question, that what happens if you take the source T mu nu to be your rotating source and put it in this IDG, and what kind of solution will you generate? And what happens is that here, a very interesting thing what happens is that essentially, again, you can because of the fact that this essentially the non-locality. Now, of course, keep in mind this in the spatial direction, these non-localities, they kind of smear it out, this ring singularity, and as a consequence, something very interesting thing happens. Now, instead of a ring singularity, you have a rotating disk, but you have a non-local region which is rotating essentially, and the non-locality, the radius of non-locality is larger than your a the radius of the ring essentially. And this kind of solution is kind of very new in general relativity, even, and also in IDG. And one of the feature which is interesting to note, that the rotation speed now, the J, in general relativity is always, whether it's you take a length theory metric or in full curve metric, the A over M or J, the rotational parameter J is always bounded below 1. But here, actually, you can enhance it, and you can enhance it by the factor, this quantity M Planck over MS the whole square, as long as MS is less than M Planck, and which is true. And so essentially your J can be much larger. Of course, having said so, this, I mean, we cannot trust it because it's still in the linearized limit. So it's not a very, nothing to do with astrophysical, rotating black holes. But even in astrophysical black holes, you can run exactly the similar kind of argument, which I have argued in that order by order. If I solve the order by order in box, even for a rotating, for the Kerr metric, what you find is that the Kerr metric is not a solution for such non-local infinite derivative theories of gravity. But we don't have any such solution like exactly like Bertotti-Robinson kind of solution in the case of rotating metric, but I hope somebody will be able to find it. Okay, so this is about the rotating case. And So once I realized that solving the solution is becoming harder and harder. So then I started asking question, what happens to the geometric properties? You can of course ask the question exactly like what is the boundary term for this non-local infinite derivative theories of gravity? And as Jens pointed out, that essentially even problem could come even with constructing a hypersurface and defining what kind of defining the all the quantities on the hypersurface, given the fact there is a non-locality. So the expectation will be even the boundary term will have some kind of fudgeness, some kind of smearness. But so keeping this in mind, I started asking this question, that what happens if you take if you look into the Israel's junction condition? And this is the work which I recently finished with Ivan Kolar, who is present, and Pepe Francesco Maldonado. He's also my PhD student. And so something very interesting thing happens, I can tell you. So I'm not going to go through all the details of your calculation. I just want to explain you through a simple example. Let's take a sheet. Let's take in 5 dimension. Let's assume this 5 dimensional. You have this we're playing with this infinite derivative theory of gravity, and you put a sheet. So you would expect to match the Israel junction condition. And this has been done in many different contexts. In the brain world context, people have done it in 2000. Gia himself had worked on many different aspects of ADS. Essentially, you can put a brain in the ADS space-time, and then you can see what are the junction conditions you get. And you try to do the same thing for infinite derivative theory of gravity. Now, irrespective of the form factor, so we kind of like shown it for a very simple action, which is like R f of box R. We don't have even Ricci tensor, and the Riemann part we don't have, just with the non-locality in the Ricci scalar. What we have found that the conditions, the Israel junction conditions now become nightmare, because now you have infinite such conditions you need to satisfy. So every order in box you need to satisfy that your curvature should vanish, the intrinsic curvature should vanish, and the intrinsic curvature tensor should vanish on the boundary in the jump, essentially. So just to give an example, as I said, in the 5-dimensional Minkowski spacetime, you place such a brain. And what you find, interestingly, is that in order to satisfy this junction condition, what it requires is the brain tension has to be 0. So it has to be tensionless brain. So without solving the full nitty-gritty details of the equations of motion, sometimes the geometric properties give you some more insight into the problem and tells you that what kind of objects can I really expect in non-local theories of gravity. So based on this, you can also ask the question, what will happen to if I tunnel? Now, tunneling problem is very similar to my satisfying the Israel junction condition. So if I go from one vacuum to another vacuum, essentially you're tunneling, and you have a true vacuum and false vacuum. Of course, many times we try to solve the problem in a thin wall limit, which will not be applicable here. But even in the thick wall limit, one can say that what happens to all these junction conditions, whether you can realize such a tunneling event or not. So anyway, so there are many things which we can perhaps learn by looking into the geometric properties, various geometric properties. Now, in the last 1 or 2 minutes, what I will entertain is just, again, is part of the speculation, but it's a worthwhile speculation, is that, okay, well, it's fair enough that we don't have the full nonlinear equations of motion, or the solution of these equations of motion, but can I really use some intuition to build something which is interesting and which can be testable? And can I really mimic a black hole? And here, the picture is very similar to what Gia has said, or in a couple of a day before yesterday, when he was talking about the corpuscular nature of the graviton, and he was trying to build black hole with the help of n graviton interactions. So something similar, you can borrow the same language here, actually. And this is something which we worked with Luca a couple of years ago, 2 years ago. Now, the question is, can we construct a non-local star? Non-local star, what I mean by the astrophysical star, like it could be solar mass or heavy system, not just a point particle with the conditions which I mentioned before. Now, such that the condition is that the gravitational potential is less than 1 here, gravitational potential is less than 1 here, but nevertheless, the system is held by its self-gravitating potential. Although it is less than 1, but it still has some gravitational potential. So this is the idea. And the idea is, again, going back to Gia's talk, again, you have n gravitons, but now the interaction is no longer local, but I'm imposing this non-local interaction. So my graviton-graviton interactions has some amount of non-locality, and very similar to the idea which he proposed, actually, that the Bekenstein entropy, if there are n gravitons, sitting here, it will be inversely proportional to the strength. And the strength gets diluted even more because the fact that the interaction vertices are weakened in the non-local case. And they are weakened by the radius, essentially, and the inverse of the radius, I call it roughly the 1/m effective. And in presence of n such particle, you can say that this m effective, so essentially the m effective is essentially nothing but the true scale of non-locality. So it was ms here, but this is the m effective, which is the entire non-local system now. They get scaled by the number of quanta you have. N is the number of, say, gravitons. And energy of each graviton is roughly here ms divided by square root of n, because you have n of n such interactions happening. And if you build upon such argument, then what you can see is that there is a scaling behavior which turns up. So m effective scales as ms by square root of n. The mass of the star or non-local object with n such gravitons scales as square root of n ms, such a way that you still satisfy this limit that ms is much below your m Planck. So this is your m Planck and this is your ms. And so for large n, you can actually obtain an astrophysical black hole limit. So the way the star of the mass of the star will be square root of n times ms. The size of the object is now inflated. It's no longer 1/ms, but it's scaled by square root of n divided by ms. So, so what will happen is that in this case, again, the size of the object will be slightly bigger than your Schwarzschild radius, and it will be bigger by the quantity epsilon. But now the good thing is that maybe we can bring it to the experimental touch. The experimental touch will be can LIGO and Virgo can put some constraint on this epsilon, on the size of the compactness of your black holes, which we have, the events which we have seen. And one place where we try to put this constraint is understanding the quasi-normal mode. Once you have the coalescence, and then when the black hole vibrates, what kind of vibrations do we have? And could it help us to put some constraint on epsilon? I didn't talk much about the information loss paradox, but maybe this is something which we can leave it for discussion session. But the interesting thing for me is always experiment. No matter whatever we say, experiment always tells us something new. This is an effort which we started with Maggio, Elisa Maggio, Luca Bonainfante, and Paolo Pani from Rome. And we took this seriously, and we tried to understand in a black hole membrane picture, could I put some constraint on this epsilon parameter? And it turns out from the first event itself, one can put some constraint. So these are the quasi-normal modes, essentially for the real part and the imaginary part. But the thing to keep in mind is that this pink region is the one which is allowed by our this GR 150914 event, which was the first event where the signal to noise ratio was quite large, around 7 to 10. And that event itself puts some constraint on the choice of this on the epsilon parameter. So you can see that for the blue line, epsilon goes for roughly 0.1 or so, you see that you are already exceeding the existing bound. So essentially, you can put already some current bound on epsilon, that epsilon has to be less than 0.1. But in terms of astrophysical black holes, 0.1 times the Schwarzschild radius could be even roughly a couple of 100 meters or even a kilometer, depending on how big your system, your masses are. Nevertheless, this is again, one has to take with a grain of salt, because we have not included the rotations and things like that. So still, this is just the indicator, not the real final answer on any of these.
Sorry, Anupam, can you summarize in 1
Sure.
minute?
So I'm very much done on spot. So one last thing I also wanted to say is that since we are in a quantum gravity workshop, now there's an opportunity for us to put the quantum gravity in an atom chip. And even in the kind of things which I have spoken today, I was talking about them building up an entanglement and all, you can actually perform such an experiment in a laboratory. It will not happen today, but maybe say 10 years, 20 years time, the technology will be sufficiently good to discuss some of these aspects. So if you, there's a workshop which will happen in ICTP in Brazil. If you want, many of you would be interested in such questions, how to witness quantum nature of gravity even in a laboratory. And maybe this will not shed much light on non-locality, but nevertheless, we are looking for some experimental evidence of quantum gravity in a tabletop experiment. So just to keep the discussion short, so there are many, many issues I have not touched upon. Various other people have discussed the initial condition problem, Hamiltonian construction, whether these systems are renormalizable or not, to what extent is UV finite, and And here, I mean, I have touched a little bit upon that whatever physics we talk about, it has to have some experimental touch, experimental connection. Otherwise, it becomes really a religion. So I think the effort should go into understanding more about the black hole, or maybe even other experimental avenues to test not only gravity, but also beyond gravity. So thank you very much for your kind attention. Thanks a lot.
Thank you. Thank you. So thank you for the very nice talk. So we are a bit late, so maybe we can just have one very short question. I think Jens or Yen, I don't know if I'm pronouncing well your name. Sorry.
Thank you. Yeah, very simple question. Thank you for your talk, Anupam. And I didn't know you could draw so well. But quick question about this conformal symmetry that you mentioned at the location of the particle. So of course we found something similar in our studies. During my PhD defense, Don Page actually mentioned this fact that any spherically symmetric and regular geometry has a vanishing biotensor around its point of symmetry. And you can just show this in normal coordinates and just by the tensorial structure of the Weil tensor and its tracelessness. So I suspect that based on what Breno has been telling us today, that in higher derivative theories, you would find something similar. And then that raises, of course, the question if this is solely due to non-locality or just higher derivative effects in your theory. And vanishing Weil tensor as a conformal symmetry, emergent conformal symmetry, do you think this is somehow related to a vanishing beta function or something like this?
Okay, I mean, so just to give one answer. So the first part of the answer, I think I can give you. So we looked into finite derivative. I think, as you mentioned, that there's some computation, but if the condition is following. So if the condition is, if you really want, so let me dig out, I have stopped sharing my slide, but nevertheless, I can tell you. So the idea is that as long as you want the curvature to be constant, and the Newtonian potentials to be, the metric potentials to be constant, it actually forces you to be conformal. Now, how you make that Newtonian, the metric potential constant is up to you. Maybe there is some 8th derivative or 9th derivative or 10th derivative theory make it, constant. But as you know that when you add up to 10th derivative, what stops you from going from 11th derivative? So essentially you have to go for infinite derivatives as far as the gravity is concerned. So I don't see any, that you stop at finite number of derivatives. It doesn't make sense. Otherwise, why not stick to only 2 derivative theory? Now, second question about the interaction, the quantum part, the right answer would be that I don't know. I have not done any calculation yet, but yeah, maybe someone who has done the calculation with this, beta function maybe. So we have done this calculation beta function, but not in the context of gravity. In gauge theories, we have done it. In a scalar QED, we have done it, but not in gravity.
Thank you.
So I cannot say much about that.
Okay, thank you. And so let's move to the next speaker, Javier Calmet. Are you here? Okay.
Hi, yes.
I see you.